Hello students, welcome to grade 12 chemistry revision lesson on introduction to chemical thermodynamics. In our today's lesson, we will learn about common thermodynamic terms, the first law of thermodynamics and thermochemistry. At the end of this lesson, you will be able to define chemical thermodynamics, classify systems as open, closed, and isolated, states the first law of thermodynamics, calculate the change in internal energy of a system, define enthalpy change. Students, if you are ready, then we will get started. Thermodynamics. The word thermodynamics resulted from two Greek words. Thermo means heat, dynamic means change. Therefore, thermodynamics is the study of energy and its transformation. Common thermodynamic terms which are frequently used in thermodynamics. One is system. System is object of study. System is specific parts of the universe which we are interested in. Examples: a solution in a beaker, a reaction vessel, a gas in a cylinder, an engine, an electrochemical cell, and so on are examples of systems. A system can be classified into either one, open system. Open system is a system which allows exchange of both matter and energy with the surrounding. For example, a beaker of water. This is an example of open system because matter can get in, matter can get out, water can evaporate. Therefore, a beaker of water is an example of open system. Closed system. Closed system is a system which allows only exchange of energy but not matter. For example, a bottle of amber water. No matter can get in or out, but you could cool it down. This is an example of closed system. The third type of system is isolated system. This is a system in which neither energy nor matter can exchange with the surrounding. For example, thermos of water. This is the best example of isolated system. Systems have properties. One, intensive properties. Intensive properties are those properties which do not depend on amount of matter. Examples: color, temperature, and density are examples of intensive properties. Two, extensive properties. Extensive properties are those properties which depend on amount of matter. For example, mass, internal energy, volume, and pressure are examples of extensive properties of a system which depend on amounts of matter. The other thermodynamic term is process. Processes are of different types: spontaneous process, non-spontaneous process, isothermal process, adiabatic process, and so on. All these are terms which are frequently used in thermodynamics. Let us see each one by one. Spontaneous process is a process which can proceed by itself without external action, without external influence. For example, heat flows from a body of high temperature to a body of low temperature. This process can proceed by itself. Iron rusts in a moist air. Again, this is an example of spontaneous process, can proceed by itself without external agents. Non-spontaneous process is the process which cannot proceed by itself. It needs external agent, external force. For example, cleaning of a room is an example of non-spontaneous process. Heat flows from a body of low temperature to a body of high temperature. This is an example of non-spontaneous process because it needs heat pumper, external agents. The first law of thermodynamics and some thermodynamic quantities. Heat denoted by the symbol Q. Heat is energy transfer between a system and its surrounding. We know that heat flows from a body of high temperature to a body of low temperature. The SI unit of heat is joule. Another unit of heat is calorie. This is the relation between calorie and joule. 1 calorie equal 4.184 joule. We can calculate heat of a substance using the formula Q equal M times C times change in temperature, where M is mass of the substance, C is specific heat capacity, and delta T is change in temperature. Heat capacity of an object or a substance is the amount of heat energy required to raise its temperature by 1 degree centigrade. Heat capacity of 1 mole of a substance is molar heat capacity. Heat capacity of 1 gram of a substance is specific heat capacity. Example, find the amount of heat required to raise the temperature of 1 gram of water from 298 Kelvin to 398 Kelvin. Given specific heat capacity of water is 4.184 joule per gram Kelvin. We can calculate heat of this by using the formula Q equal M times C times change in temperature. Mass of this is 1 gram equal 1 gram times C is specific capacity of water, which is 4.184 joule per gram Kelvin times change in temperature is final temperature minus initial temperature, which is 398 Kelvin minus 298 Kelvin is 100 Kelvin. 100 Kelvin. Now Q equal gram will be cancelled by gram, Kelvin by Kelvin. We are left with joule, which is the units of heat. Therefore, 1 times 4.184 times 100 equal 418.4 joule. Work, just like heat, is energy transfer between a system and its surrounding. Here we will consider only pressure volume work. Consider we have a gas confined in a cylindrical container that is fitted with a movable piston. Work by definition equal force times distance. Here the distance is delta H because a piston moves. Delta H equal force times delta H. Force in terms of pressure is P times A. Force equal pressure times area. Pressure times area times delta H. This is the same as pressure times base area of the piston, base area of the piston times height gives change in volume delta V equal P times change in volume. Now this is the magnitude of this work, which is pressure volume work. The sign of work is negative, work equal minus P times change in volume, because the system moves a piston against the applied pressure. Work is done by the system. The system lose energy as work. Work equal minus P times change in volume, which is known as expansion work. Expansion, the gas expand, expansion work. See? From the system's point of view, the sign of pressure times change in volume is negative, negative work, work done by the system. The first law of thermodynamics. The first law of thermodynamics is restatement of the law of conservation of energy. The law of conservation of energy states that energy is neither created nor destroyed, but transferred from the system into the surrounding, or from the surrounding into the system. The first law of thermodynamics states the total amount of energy in the universe is constant. We can write this as in total energy E of the system plus change in energy of the surrounding equal 0, or change in energy of the system equal the negative of change in energy of the surrounding is constant in the universe. The first law of thermodynamics, often formulated by stating change in internal energy equal heat absorbed by the system plus work done on the system, delta E equal Q plus W. For example, if a gas absorbs 50 kilojoule of heat and does 25 kilojoule of work, what will be the change in internal energy? You are asked to calculate internal energy for this process. Now, from the first law of thermodynamics, we have change in internal energy equal Q plus W. Here, a gas absorbs 50 kilojoule of heat. The system gain energy as heat. The sign of Q is positive plus 50 kilojoule equal 15 kilojoule plus, and does now the system lose energy as work. Therefore, W is minus 25 kilojoule, minus 25 kilojoule. 50 kilojoule minus 25 kilojoule equal 25 kilojoule. Internal energy of the system increased by 25 kilojoule. Example 2, 450 joule of heat are transferred from a system and its internal energy decreases by 60 joule. Find work done by or on the system. You are asked to calculate W, work done by or on the system. Now, from the first law of thermodynamics, we have this delta E equal Q plus W. Change in internal energy of this system is decreased by 60 joule. Delta E, change in internal energy, is minus 60 joule. 450 joule of heat are transferred. Now the system lose energy as heat. Q is minus 450 joule. Q equal minus 450 joule. Now, from the first law of thermodynamics, we have this relation, delta E equal Q plus W. From this, W equal delta E minus Q equal W. Delta E is minus 16 joule, minus 60 joule, minus Q is minus 450 joule. Minus minus become plus 450 joule equal W. From this W equal minus 60 joule plus 450 joule is 390 joule plus 390 joule, you see. Now work done on the system. The system gain energy as work which is 390 joule. Thermochemistry. Thermochemistry is the study of energy changes that occur during chemical reaction. Heat of reaction. Heat of reaction is the total amount of heat energy that is involved or absorbed by a system at a particular temperature because of chemical reaction. From the first law of thermodynamics, we have this: change in internal energy equal Q plus W equal Q plus, if the work is pressure volume work, we can write this as Q plus P times change in volume. If a reaction occurs at constant volume, now change in volume of the system is 0. Therefore, delta in equal Q. Delta in equal Q, heat absorbed or released by the system at constant volume, you see. Change in internal energy of the system equal heat absorbed or released by the system at constant volume if a reaction occurs at constant volume. Enthalpy denoted by the symbol H, capital H. Now enthalpy is the heat absorbed or released by a system at constant pressure. The formal definition of enthalpy is this. Formal definition of enthalpy: H equal E plus, formal definition of enthalpy, E plus pressure times volume. Now initial enthalpy equal HI. Initial enthalpy equal HI equal initial internal energy plus pressure times initial volume VI. Final enthalpy H final equal E final plus pressure is constant P times final volume. Now the change in enthalpy delta H equal H final minus H initial equal final enthalpy is E final plus pressure times V final equal E final plus pressure times final volume minus initial enthalpy is initial internal energy plus pressure is constant times initial volume. Now this is minus EI minus pressure times V initial. Now the change in enthalpy delta H equal E final minus E initial is change in internal energy delta E plus, you can factor out pressure because pressure is constant, P into V final minus V initial is change in volume. Therefore, the change in enthalpy delta H equal change in internal energy plus P times change in volume. You see? Change in enthalpy equal change in internal energy plus pressure times change in volume. We can write this as delta H equal change in internal energy from the first law of thermodynamics is Q plus W plus P times change in volume. If work is pressure volume work, therefore this is the same as Q minus P times change in volume plus P times change in volume. Now P times change in volume minus plus P times change in volume is 0. This term is 0. Therefore, the change in enthalpy delta H equal heat absorbed or released by the system at constant pressure. You see, the change in enthalpy equal heat absorbed or released by the system at constant pressure. Some properties of enthalpy. 1. Enthalpy is an extensive property. Enthalpy depends on amount. Look at this reaction. Half nitrogen gas plus 3/2 H2 gas gives 1 mole of ammonia. Now delta H for this reaction, enthalpy change for this reaction is minus 46 kilojoule per mole. Now the forward reaction is exothermic. If you multiply this reaction by 2, you have to multiply enthalpy change by 2. Therefore, if this reaction is multiplied by 2, now the change in enthalpy delta H equal 2 times minus 46 kilojoule per mole, which is minus 92 kilojoule per mole. You see? Therefore, enthalpy is an extensive property. It depends on amount. 2. The enthalpy change for the reaction is equal in magnitude but opposite in sign if the reaction is reversed. Again, look at this reaction. The forward reaction is exothermic. If you reverse this reaction, then the change in enthalpy is the negative of this. The reverse reaction is endothermic. Therefore, the enthalpy change for the reaction is equal in magnitude but opposite in sign when the reaction is reversed. 3. The enthalpy change for a reaction depends on the states of the reactants and products. Therefore, the states of the reactants and products must be specified. For example, methane gas, combustion of methane, CH4 gas plus CO2 gas gives carbon dioxide gas plus water gas. Delta H for this reaction is minus 802 kilojoule. You see? If the states of water is liquid, now delta H of this reaction is different from minus 802 kilojoule. Therefore, enthalpy change delta H depend on the states of reactants and products. These are some properties of enthalpy. Example, when 1 mole of methane is burned at constant pressure, 890 kilojoule of energy is released as heat. What will be the value of delta H for the process in which 10 gram sample of methane is burned at constant pressure? You see, when 1 mole of methane is burned, 890 kilojoule of energy is released. What does this mean? 1 mole of methane, 1 mole methane, CH4, which has a mass of carbon 12, hydrogen 4, 16 gram, release 819 kilojoule minus 890 kilojoule of energy. If 10 gram sample of methane is burned, how much heat energy is released to the surrounding? 10 gram release X kilojoule of energy. From this, delta H equal heat absorbed or released by the system at constant pressure, which is 10 times minus 890 divided by 16. 10 times minus 890 divided by 16 equal minus 556.25 kilojoules. When 10 gram of methane is burned, minus 556.25 kilojoule of energy is released to the surrounding. Therefore, enthalpy change equal heat released by the system at constant pressure. Standard states. We know that most substances are found to be stable at a temperature of 25 degrees centigrade and a pressure of 1 atmosphere. Therefore, the standard state for a substance is the most stable form at 25 degrees centigrade and 1 atmosphere. For reactions of the type AM plus B to form CC plus DD, change in enthalpy delta H of the reaction equal C times delta H naught formation of C plus D times delta H naught formation of D minus A times delta H naught formation of A minus B times delta H naught formation of B. Standard enthalpies of formation. Standard enthalpies of formation of an element in its most stable state is 0. See, delta H naught formation for an element equal 0. For an element equal 0. For example, the standard enthalpies of formation of ammonia, water and nitrogen monoxide are minus 46.2, minus 241.8 and 90.3 kilojoule per mole respectively. Calculate the enthalpy of this reaction. Students, delta H naught formation of an element, or the standard enthalpies of formation of an element, by definition is 0. What is delta H naught of the reaction for this reaction? Delta H naught of the reaction, standard enthalpies of the reaction, delta H naught of the reaction equal 6 times delta H naught formation of water. Delta H naught formation of water is minus 241.8, minus 241.8 kilojoule per mole, plus 4 times delta H naught formation of nitrogen monoxide. Nitrogen monoxide is 19.3 kilojoule, 19.3 kilojoule, minus 4 times delta H naught formation of ammonia is minus 46.2. 4 times delta H naught formation of ammonia is minus 46.2 kilojoule, minus 46.2 kilojoule. Minus 5 times delta H naught formation of oxygen is 0, because the standard enthalpies of formation of an element by definition is 0. Now, delta H naught of this reaction equal 6 times this plus 4 times 90.3 kilojoule minus 4 times minus 46.2 kilojoule gives minus 904.8 kilojoule. This is the standard enthalpies of this reaction. Students, in our today's lesson, we learned the definition of thermodynamics. Thermodynamics is the study of energy and its transformation. We discussed common thermodynamic terms such as system, intensive and extensive properties of a system, spontaneous process and non-spontaneous process. As we said, spontaneous process is the process which can proceed by itself. Non-spontaneous process is the process which cannot proceed by itself. It needs external force, external agent. Thermochemistry. Thermochemistry is the study of energy absorbed or released by a system. This brings us to the end of our today's lesson. Until next time, goodbye.